But hello everyone, this will be another LeetCode problem. I also haven't solved it before. Okay, I have a node reference of binary search tree and a key. Delete the node with the given key in the binary search tree. Return the root node reference, possibly updated, of the binary search tree. Search for node to remove if the node is found. Delete the node. Okay, if the node is found. So I see a few possible things to consider, but let's talk about that when we get to the test part. First, let's figure out the signature node, which is tree node, and I will just say that is optional tree node, so it may be none. And then we are also returning an optional tree node. So tests. First of all, let's say that it's an empty tree and whatever is the key. Actually, I forgot. Here we also have key, which I'm assuming is an integer, but it can be whatever the type of values that our tree node can store. Let's just assume that it's integer for simplicity. Now, let's talk about some other options. So here, let's say it was 1. Let's say that we have a 2, 1, 3 binary search tree, and we are returning, we need to remove the node 4. So in this scenario, we are just returning the same tree. But what if we want to remove 3, let's say? Then we just remove 3, that's fine. What if we want to remove 2, which is the root of the tree? So it can be whatever. We can either put 1 on the first place or 3 on the first place. But let's just go with 1. And then, are there any other corner cases? So something that doesn't exist. Okay, there is another corner case where, let's say, we have another node which is 2. So let's say it will be 2 and then 2 and then 3. Yeah, 2 to 3. Let's say it's this, right? So either it's impossible or we just remove the first such available node. I think let's just remove the first of such available nodes. Okay, so now the solution. So we can search for an item in a binary search tree in of log n time, where n, let's define it as total number of nodes, and at worst it will be of n. Will it? Yeah, if the tree is unbalanced, it can be of n. But should we assume balanced tree? Let's not care about this, because either way our later removal, okay, how long will it actually take? Yeah, I think removal, search, and of n in unbalanced. So removal will be of 1. Will it always be of 1? Yes, because we are removing something, and then we have something in the subtree that we are removing, so that we are removing parent. Let's assume that it's a parent of some subtree. So then we can choose either the left or the right value of the subtree. and it will be the suitable parent. So then for this either right or left value, we will need to rearrange things. But okay, there is this issue that we can go further and further down. We might need to go further and further down below to update our tree structure, because what if we are updating a subtree, removing a parent in a subtree that is a full subtree? So basically each node has two children. In such case, if we remove the parent, then some node needs to go to the place of this parent, and then we need to do this recursively. We need to update all of this until the end. So the removal will be not of 1, it will be of log n. Also, if the tree is balanced, but it can be up to of n if the tree is like a very specific unbalanced thing and we get unlucky. But overall, the solution is straightforward. So first we need to find this node, and we will just traverse the binary search tree. If a particular node has value that is bigger than the key, then we go to the left child. If it's smaller, then we go to the right child. If it's equals, then we choose this particular node to update. So what does it mean that we need to update, right? So search will be standard, but updating need to keep track of the parent. So we can write a recursive function that applies to each node, and if there is a left node and the right node, then we can arbitrarily choose between those. Okay, maybe I should also mention that if we are especially clever about how we are sorting those nodes and we keep the track of how many nodes are there under each subtree, we can do this removal in a non-arbitrary way, but in such a way that keeps tree closest to being balanced. But since we are not tracking this, we would need to change data structure, or like at least what we are storing in the nodes here. So we are not doing that. We won't be doing that. We will just arbitrarily choose left, let's say, always, as the node that we need to untangle. So if we have two children, we choose the left of those and we put it in the parent, and then we need to update the right child, and then we need to continue recursively to iterate over this node for, like, if the left node is a parent of some other nodes, we will need to continue doing that. So yeah, that's the recursive function, and now we just need to implement this. Overall, I mentioned the running time of this solution, and it will be of log n up to of n space. So we will be using recursion, so recursive stack equal to runtime. So if it's of log n runtime, then it will be of n space, because that's the amount of recursive call that we need to do, and in each of those calls we will do of one amount of operations. Now let me implement what I was talking about so far. Okay, so implementation. First of all, let's right away figure out this case where if root is none, then return root. Basically, we're returning none back, because whatever we have in the key, we cannot remove anything. Then I think we will need to do a trick here. We will need to create a dummy parent. So so that we always have like if we need to remove the root of the tree itself, we will need to still have some parent to refer back to so that we can update the whole tree and the whole tree structure. So dummy equals to tree node, and value equals star. I don't know yet, I haven't figured out exactly how I will decide whether it's the root that was removed or not. Maybe I should just do a comparison, so value can be anything, and I can just do a comparison, like if this node that I have found in the process of search is root, then I will do it one way, otherwise in a different way, but for now, okay, let's keep it as none, everything, right? Okay, but the left will not be none, the left will be pointing to root. Now I think, let me try to be careful and let me create a tree that I will be updating. So let's do it 5, 3, 6, 1, 4. Okay, so let's say we have this tree, and let's say our k is equal to 5. So the first step of the algorithm will be that we create a dummy node here that is pointing to our 5. Then we search for 5, and we just do it iteratively. So okay, we have found our 5, and now we need to remove 5. So how do we remove 5? First of all, we need to create a new tree node. Okay, so we will start with D. Then we will be creating a new tree node, so N. And then for this N, so we will choose the previous parent. And for this parent, we will update the left pointer that it now points to N. Then we will update the parent itself to N. And then we will start updating. We will need to have the real child as it was before, so it will be 6. And then we will need to update the 3. 3 will be the left. Oh, 3 will become the parent. So now I will be bringing this parent here. Okay, yeah, I did this incorrectly or not. So we will be creating a new node, and then we just need to update this node 3. Yeah, so we take the value of the left child, and if this value is none, we update it here, and it becomes 3. Yeah, so it becomes 3. And then we continue iteration on, like, we basically defining the function of remove, and then it's N, and then again we will be updating this. Oh, but I cannot put 3 here. That's something that I didn't think about, right? So it was the right value to put here, but now it cannot be the right value because there is a bigger value down these trees. Actually, it might mean that I don't need to change. Yes, I just need to find the biggest value in the subtree. In the left subtree, I find the biggest value, and I put it as my parent now. So it will not be 3 that I will be putting here. It will be 4 that I'm putting here. And I will be basically removing this 4 and putting it up here. So it will stay here, 3 will stay here. So first I find the node, then I find the biggest value node that I have, I remove it, I pop it, I put this value here, and I just update the node. So yes, then we still need to traverse the whole tree to find the biggest possible node after this one, but the biggest possible node in the left subtree, we can find it in O of log n. So it's still, removal will take us O of log n in a balanced tree, but we don't need to do this function application recursively. We just need to do it once, because the biggest node in the left subtree is a node that is guaranteed to be bigger than all the other nodes, so we can put it as a parent of the whole left subtree after removing it itself. So then the question becomes, okay, what if this this parent, this 4, what if it also had another child? Let's say it's the biggest one in the left subtree, but it also had a child on the left. So let's say this was 2 and this had a child of 3, right? So how do we do in this scenario? So everything here will be, yes, so if this 4 has children, so if it has right child, it will not be the biggest node in this subtree. So we will, it cannot have right child, but it can have left child. And if it has left child, it is guaranteed to be, like, everything in the left subtree of this 4 is guaranteed to be bigger than this 2 parent up here. So because 2 is a parent of everything that is in this 4 subtree. So we basically can just get the node on the left. So we find the biggest node in the left subtree. We take its left child, and we put it in the place of the parent, and then we put the parent in the place of this starting node, and then that's it. We just need to figure out, oh yeah, we will be returning the left node of the dummy node, so we don't need to figure anything out, like with these values or anything. Okay, sounds good. So now we have an idea about how we can do our iterations. First, let's now find the node. So candidate is root. Is not none. Okay, so if candidate value is bigger than key, we need to go to the left essentially. Candidate equals candidate left. Else, no, L if candidate equals candidate value is smaller than key. Oops. Candidate equals candidate right. And then finally else key node equals candidate. Okay, so then if candidate is none, so what it means here is that we have found, we have traversed the whole tree, and eventually we got out of this loop because of this row. So if it's none, it means that we haven't found the key, so we need to return a root because we are not removing anything. Else, we need to go we now need to go and actually find the biggest value. Okay, my timer works, so it means that we have spent 20 minutes. Let's spend a few more. So now we need to find the biggest node. Okay, so oh yeah, what if we don't have anything on the left? That's another thing, right? So what if we just had something like this and we needed to remove 5? So we in such case we would need to find everything in a mirror. I'm trying to think whether there is a more elegant solution, because here I would need to find like either the biggest node of the left subtree or the smallest of the right subtree, or it's also possible that the node will be the only one, right? So what if it's just 5 and we are looking for 5? Those are also good questions. Yeah, okay, I don't see any like elegant solution. I just need to check. Okay, if key node, now it's definitely exists because key node equals candidate, and then we break from the cycle. So if key node left is not none, well, okay, biggest equals key node left, well, biggest right is not none, biggest equals biggest right. Okay, so now if it's not none, we just need to do the key operation. Okay, we also need to store the previous. Okay, previous equals key node, biggest. Okay, previous equals biggest, and biggest equals biggest right. So now we have traversed through the whole tree and we have found the biggest node, and we can now make it the parent. So we can make it the node that we are removing, right? So we just need to find this value. We need to remove this node. So how do we remove this node? If biggest left is not none, then we say that previous right equals biggest left. That's one scenario. Then else biggest left is not none, previous right is equal to biggest left. Now if biggest left is none, then we basically say that previous right is, actually yes, whatever we do, previous right is equal biggest left. The thing is, if it's none, then we need to, if biggest left is none, then we do make previous right to be equal to none. If it's not none, we make it equal to whatever that is. Okay. Sorry, I'm getting a bit distracted by my son, but it's alright, I'm guessing. Okay, now back to it. This is us just removing this node, but now we need to make this parent that we have been removing. Okay, we just need to key node. Okay, here, before we are removing, key node val equals list val. Okay, this is one update. Oops. Yeah, this is if the key node left is not none. Else if key node right is not none, we do the same thing, but we now need to do biggest smallest. Is key node right? Well, smallest left is not none. Smallest left, smallest, and previous left, smallest right. Okay, else there is just one option, that we actually are removing the node that doesn't have any, we're removing the node that doesn't have any children. So yeah, the problem is that if we are removing some parent, some key node, and we are removing we are putting some value on this place, then we can find this value and we can update the tree. But if we are not putting any value in this place, because we don't have children and we just need to remove this node, so it just means that the parent needs to be updated to point to none instead of this node. So we also have to do previous equals done here, and previous equal candidate equal, and here previous equal candidate. Okay, I am redefining it here, so okay, here we are updating, but otherwise we are leaving it be. Okay, so now we have previous key, and in case where we are removing the leaf node, we just need to do previous Oh damn. We also need to figure out whether it's right or left node that we are removing. Okay, so else if previous key right node is not none and previous key right value equals to key, then it means that we're removing right, so previous right should point to none. Else previous key left is equal to none. Wow, that's a lot of code. I'm probably missing some more elegant implementation, and I would need to like try all of these possible test cases to figure out if I'm doing things correctly. But let's check just a few of those, right? So let's first get this one, right? And we are searching for 5. So we will be first going to, like, assuming that this code for writing the node is right, we will be pointing this as a previous key, and this will be the pointer to the node that we are updating. So then we will be traversing, like, here is if key node left is not none, we will be choosing previous as key node, so previous will be 5, and then biggest will be 3, which is fair, and then we will be doing iteration to the right, to the right, to the right until we get to 4. Okay, so, and our previous will be updated to 3 here, fine. So we will be updating this so that it points to none from 3, and this will be updated to 4, and yes, it looks correct. And also we will be updating, the only changes that we will be updating with 3, this value, if we're removing 5 here and 4 will be put here, which is also fine. But now let's say we are not doing that and we need to go to the right, so it's mirrored, so it's also fine. And finally, let's say we just need to return 5 from the root. Okay, and return the root node reference, possibly updated. Okay, return the dummy left. Is it dummy node? Yes, dummy left. That's what we are returning. Actually, since we are not updating, we are not creating new. Oh, we still need to do previous key equal to dummy, right? Yes, because we will need to update if we're removing the root node in exactly this scenario. We will be removing this altogether, so we will need to make dummy previous key right is not none, and previous key right for equals key. Okay, it's none. Otherwise, previous key left is none. Yes, it looks good. Let me try to submit the solution. Okay. I have okay, it says that I'm incorrect because I'm returning this specifically. I'm returning this. Oh yeah, I am incorrect because we were removing 3. So we are removing 3, and we need to But yeah, the issue that I have in my code, it's also kind of correct, but I have botched. So there are two possible approaches here, right? Like either you will be returning the node that points like 5, 2, 4, or 5, 4, 2. Yeah, that is also another valid answer. So what I'm doing in my code, I'm searching for the biggest node here. So this is fair. I will be putting 4 here. So it's 5. I'm removing this node. No, I'm removing this node. So I'm removing this. Actually, I need to put 2 here. Yes, that's good. So I'm updating this node to 2. Five is pointing to. Obviously, I need a few minutes to figure this out. So I'm removing 3. I have left and right node. I'm updating this to 2. So this will. Oh. Yeah, I think there is also a different corner keys that I didn't actually think about. What if I need to remove exactly like in this situation, like I have the node and I need to remove something like 5, then 2 and 6, or 3 and 6, right? So what I'm doing is I remove this node 3, and now this 5 node should be pointing. I'm removing 5, I'm putting 3 in this 5 place, but now this 5 should be pointing to nothing place. So basically key node left should be none, but it's not updated to none. Yeah, I need to change something about the code. Is there a way to do this more elegantly? والله الحمد لله والله خابرتني من يوم جماعة الأمنيات يوم الغرامات مخابرتين يوم الغرامات الحمد لله هسه خلصنا نفسات الانتظار. Just adding more ugly code. والله جبت تقريبا ساعة ونص تنصح الطيارة. كيف ما كيف التنوير تقدر تستخدم مصادر ما تنصح. Okay, let me take a step back and think about this problem a little bit differently. Let me, instead of updating the values, maybe restructure the whole tree. Okay, I obviously need to write some more code. I have some ideas about this, but I don't like how it looks. So yeah, for now I will just leave it be. and we'll I don't want to leave at this stage. Okay, I already spent 40 minutes. So I don't want to leave it at that. Let's try to iterate again on something more elegant. What I'm thinking about right now is, what if instead of like updating the values, we were just rearranging nodes? So we find the node, let's say here we search, we always have some like previous node that we search. So we can use this function search. We have the node that is parent. And we need to cut the node. So we are doing the same things, but instead of updating the values of the nodes, we rearrange the nodes themselves. So for example here, right, we do previous key, the node I came from, sorry, just saw there was a message on the chat, but I don't know how to open the chat. Okay, so if keynote left is none, traceable keynote. Yeah, the problem is that let me do ugly code. Did iter false. Did iter equals true. So here we will do iteration. If did iterations, then this code will be right. But else, what this means is that we have never gone to the step on the right. So our parent is still the node where we are actually at the left child. So it means that previous left will be biggest left. And okay, it will be either way keynote bell. And now we just need to do the same ugly thing here. Did is false. Did answer equals true. And now if did meter else okay, now that's crazy, but I'm really interested to know what's the right elegant solution there that I'm obviously not seeing. Yep, at least it got accepted, which is always nice, but it was brutal. And figuring out this corner keys in interview scenario would have been really tough. Probably I would need to have a specific test case pointed out, because here they would just say, okay, what's the issue with this code? And I would have no idea. They would need to give me a hint, and hopefully there is a more elegant